Yay, more equilibrium. I'm telling you, if you just lock down on the idea that all of this stuff is equilibrium, there's just some details around that. You fill in those details, the math problems are all very, very similar. Actually, this chapter will introduce some shortcuts. The Henderson-Hasselbalch equation means that there's an ice table that you don't have to do. Although you could do it with an ice table also. Oh yeah, this is a good quote. In the strictly scientific sense of the word, insolubility does not exist. Even though substances characterized by the most obstinate resistance to the solvent action of water may be properly designated as extraordinarily difficult of solution, not as insoluble. So a lot of the idea for this chapter, we're going to talk about solubility of things, is everything is soluble a little bit. Everything. How much is a little bit? We'll see. I think one of the things, it's like 10 to the negative 35 or something. It's just like, that's less than, right? A mole is 10 to the positive 23. We're like beyond that by several orders of magnitude negative. It's just, it's still not zero. It's technically still not zero. We will also talk about buffers in this chapter. So antifreeze is dangerous, especially to animals, because it smells sweet, and from what I've been told, it tastes sweet, which is enticing to animals. And so they come up and they drink some of it. And when their body starts to metabolize it, it also produces glycolic acid. That glycolic acid then, well, it's an acid, starts to lower the blood's pH. And your blood has an ability to buffer or resist some change in pH, but that's only up to a point. So if you get too much of this, then that buffer factor gets overwhelmed, the pH starts to drop. So like in humans, it's like 7.36 to 7.42. If you are outside of that range, you can die. It's a very narrow range. Fortunately, our bodies are pretty good at staying in that range. There's something else I don't want to. Yeah, so it turns into glycolic acid. Blood pH is maintained by buffers. So a buffer is a chemical system that resists pH changes because it can neutralize acid or base that gets added. And one of the important ones in blood is carbonic acid and bicarbonate ion. So those two together maintain your blood pH. This is also the only way that your body knows if there's not enough oxygen, because it doesn't actually know if there's not enough oxygen. It just knows if there's too much CO2. If there's too much CO2, then the carbonic acid in your blood increases. And your blood pH starts to become more acidic, which is what makes other, it's like if you were, I'm sorry for claustrophobic, like in a small room and there was no other outside air, like eventually it's your own CO2 that builds up. And then your body knows that you're running out of oxygen. In situations where it's not CO2 that removes all of the oxygen, your body has no signals for low oxygen, only for high CO2. So if it's nitrogen or helium, one of the horror stories or like horror situations that they told us about in grad school, I took a class with NMR machines, really, really large NMR machines. And they're cooled with liquid helium because they have superconducting magnets. If that liquid helium quenches and then all turns into a gas at the same time, it will push all of the other air out of the room. And then you only have a very short amount of time before you run out of oxygen in that room. But again, if it's not CO2, then your body doesn't know. Because really what you feel when you're trying to hold your breath for a long time is that buildup and the decrease in pH of your blood. So antifreeze does that by essentially, well, your liver processing it does that. So in acidosis, again, if the pH builds up too high, look at this, Le Chatelier's principle. They build up in excess in H+. This is this is hemoglobin, right? So hemoglobin with the oxygen, which it needs to do to carry it to other parts of your body. If this gets pushed to the left, then the hemoglobin equilibrium gets shifted away from picking up oxygen, and it can't pick up oxygen as efficiently. So one way actually to treat for this and even methanol poisoning is the administration of ethanol, which I always remember because there was an episode of House, and there was this, I think it was like a prison inmate, and he drank printer toner, which had a bunch of methanol in it. He was like dying, and then like House comes in and he gives the guy a shot of vodka, and the guy gets better. And they were like, whoa, you're crazy. What actually happens is ethanol is an alcohol, ethylene glycol is an alcohol. In your liver, if you have a bunch of ethanol around, it will outcompete the ethylene glycol because it's actually the ethylene glycol getting processed into the glycolic acid that's dangerous. So if you can just saturate the liver with alcohol, ethanol, it'll process that first, and then your body can get rid of the ethylene glycol without processing it and making it dangerous. That's just a fun fact. I guess that, in a sense, is kind of not really an equilibrium. It's competition. All right, so buffers. Buffers are super important. We use buffers a lot. They resist pH change using a lot of the concepts that we've covered in the previous 2 chapters. So they resist pH change. We'll talk about how they do that. Buffers have to contain a significant amount of a weak acid and its conjugate base. Or it could be a weak base and its conjugate acid. Just the weak acid or weak base alone doesn't have enough of the conjugate to act as a buffer. And we calculated this. Right? If you calculate for any acid, like even if it's 0.10 molar acetic acid equals H2O, you're going to get some of the acetate, the conjugate base, but it's going to be a really tiny amount because the Ka of this is something like 3.5 times 10 to the negative 6. I don't remember if that's exactly that number. But really only a small amount of it's going to ionize. And so just the acid by itself doesn't have enough base that gets produced to act like a buffer and to counteract any acid or base that gets added. So we need to have both of these. So if I had initially 0.1 molar of each of these, that would be a buffer solution. If I add acid to that, then I will use up some of my base. But since there's already a high concentration over here, that suppresses that. So the acid gets neutralized and my equilibrium shifts just a little bit. If I add any base, it'll react with the acid and create more, but it'll again end up buffering the solution. Because it's like it neutralizes, but then because there's a lot of the other ion, it's suppressed so it doesn't just keep going. There's brakes on the system. So what makes this really, really different from anything that we were doing before is that before we said we're starting with just the weak acid, how much H3O plus and base gets produced. Here we're saying I'm starting with both. Like I'm putting in acetic acid and sodium acetate in significant concentrations. So we'll have all of those floating around in solution. So which of these solutions would be a buffer? So for a solution to be a buffer solution, we have to have a weak acid plus its conjugate base. Not just any base, but its conjugate base. Yeah, it's D. Because A, HNO2 is a weak acid, but it's paired up with a strong acid. So can't be that. B looks like it might be, except that nitric acid is a strong acid. So you add this in, and it's just going to completely ionize, and then this will have no effect on the pH. So it can't be B. C, we do have a weak acid, but then this is neutral. So not C. Surprised there wasn't a trickier one in there. Okay, before we get to calculating anything, I think we'll save that for Wednesday. Yeah, 10:58 is close enough. To talk about buffers. So buffers are solutions of conjugate acid, conjugate base pairs. Like in blood, there's carbonic acid and the carbonate or bicarbonate, which we looked at this on Monday. So carbonic acid, bicarbonate, those two things work together to buffer the pH of our blood, of everyone's blood. It keeps the pH in a reasonable range because the range that keeps you alive is a narrow range. So it needs to stay in that narrow range. It's important to have both parts of the same system. I should say somewhere the common ion effect. It's because of this common ion effect. So if I have, like here, acetic acid and sodium acetate, which we're going to use as examples a lot, because they're just common ones. The equation for this would be like H2, not H2, HC2H3O2 plus H2O equilibrium with H3O plus C2H3O2 minus. There's an equilibrium here. And so if I change the pH of this solution, if I add more acid, add more base, it'll cause this to either shift to the left or shift to the right. But because there's already concentrations of these things present in a buffer solution, it resists that change more than if I had separate bases or acids. Because for this, if this concentration goes up and it shifts the reaction to the left, there's already some concentration here. There's already some concentration here. And so the pH ends up not changing very much. And we haven't done any calculations yet, but you'll see when we do some calculations, it really doesn't change much at all. So the reason that a lot of these aren't buffers, well, actually for two of these, I think they were strong acids. Strong acid, this is a neutral salt. I guess none of these were just like different acids and bases. Like here we have a weak acid, but we don't have a conjugate. So only the pair of the weak acid and its conjugate weak base can act as buffers. So to calculate the pH of a buffer solution, we're going to be talking about sort of several different ranges. So if you had lab yesterday, or if you've been writing your pre-lab for the polyprotic acid, diprotic acid, you get a pH graph that looks like this. pH increases, NaOH added. When we're talking about buffers, wait, this goes, whoops. This would actually go up again. It's this flat region on the curve that we're talking about. So that's where we have a buffer. That's where our buffer is resisting a change in pH, which is why the curve is so flat there. It does go up and down a little bit, but for the most part, it's flat. So inside of that buffer region, we can use ice tables. So we want to calculate the pH of a buffer solution that is, bless you, 0.2 molar in acetic acid, 0.1 molar in sodium acetate. Treat these as initial concentrations. Even though it doesn't say that they're initial concentrations, it's the concentration sort of each that's added. The actual concentrations after it equilibrates will shift and tell us what the pH is. Especially since, as we write this in, so I've got HC2H3O2 plus water. That gives me H3O plus C2H3O2 minus. So I've got an initial concentration of 0.2 molar acetic acid, 0.1 molar sodium acetate. Not writing in the acetate because then it wouldn't be balanced, and the sodium doesn't really matter. It's a spectator ion. What's the concentration of water? It is irrelevant, correct. The actual molarity is like 55.5, but it doesn't matter. Do you want a Jolly Rancher? Dang it, I gotta get different candy. Maybe I could throw out money. No, wait, just pennies. Yeah, so that doesn't matter. What's the initial concentration of H3O plus? There's a technical answer and there's a practical answer. Practical answer is 0. Technically, like 10 to the minus 7, but we're not going to worry about that. Practically, it's 0. So initial change, equilibrium. Which way is this going to shift? To the right. Why is it going to shift to the right? There's no H3O plus over there. It has to shift to the right. I am so tired that this morning when I was going through these problems as practice, just to make sure I knew how they were going to go, I actually wrote it the wrong way because I was like, oh, it's a very small k. And then I started writing in 0 minus x, and I'm like, wait, can't do that. So pay attention. 0 means that I cannot take anything away from it. It has to be added to the other side. Cool. So that's where we'll be at equilibrium. Can I assume that x is going to be small? Probably. It's not going to move very much. I mean, we're already kind of like, aside from the 0, like there's already more reactants than products. But also because I've got stuff on both sides, the amount that this actually shifts is going to be pretty small. And it's almost always easy enough to just say, well, we'll assume it's 0, we'll check later. We can always come back and do the quadratic formula. So now it's the products over reactants, so x times 0.1 divided by 0.2. So times 0.2 divided by 0.1. So this is 0.123436 equals x. And the negative log of that, 23436, which will give me the pH, is a 4.44. that is one way to do these. Always works. Just a nice table. I think the only thing that maybe is a little bit different is that it's not saying that it's the initial concentrations of our acid and base, but it is just another equilibrium problem. I do personally really like the Henderson-Hasselbalch equation because it's a simpler equation and doesn't require writing out an ice table. There's an asterisk on when you can use it. Have to be in the buffer region. If you leave the buffer region, you can't calculate anything with the Henderson-Hasselbalch equation. So real quick, to derive this sort of for a generic acid-base equation, just need to write out what is the expression, the equilibrium expression. So concentration of H3O plus, concentration of A minus divided by the concentration of the acid. Standard stuff. That's like chapter 15, 16? 16. To get the Henderson-Hasselbalch equation, we can take the negative log of both sides. As with so many things, acids and bases, taking the negative log makes it a little simpler. So negative log of the Ka is the pKa. Negative log of H3O plus is pH. I can say that's plus the negative log of A minus over HA, because I can't really take those and turn them into anything nicer. And if we're trying to solve for pH, which most of the time we are, then I can rearrange this a little bit and get pKa plus the log of the base over the acid. Oops. Equals pH. And that's the Henderson-Hasselbalch equation. Functionally, it does the same thing that we were doing with an equilibrium expression. And actually, if we compare this equilibrium expression, I guess there's some, it's like the concentration, this is the concentration of my base, this is the concentration of my acid. So this is A minus, this is HA, this is H3O plus, which if I took the negative log of everything would be my pH. This is Ka, but if I take the pKa. So the reason that the Henderson-Hasselbalch equation works is because we can assume that X is small enough that it just falls out of the equation. We can just ignore it. So I'm not going to ask you to derive the Henderson-Hasselbalch equation. So one of the caveats is that it only works when the X is small approximation is valid, which as long as we have initial concentrations of acid and base that aren't too small, so they have to be like 100 to 1,000 times bigger than K. So for a concentration of 0.1, whoops, if my concentration equals 0.1, then K needs to be at least 10 to the negative 3, would be 100 times 10 to the negative 4. would be 1,000 times smaller. So most of the time, we're working with concentrations that are at least that big, if not bigger. And all else failing, you can use the equilibrium approach. Will always work. So to show that these both come out with the same thing, we can do both of them side by side. I should say for buffers, the chemical equation that I write out is always going to be the chemical equation for the acid. Especially if you're given a Ka, because the Ka is for the acid. If we were talking about a base, we could do it for the Kb, but then the Kb would be given. And so we would do it for the equation for Kb. So we can just use Kb instead of having to convert it. So here, this is going to be HCN plus H2O, H3O plus Cn minus, which is the conjugate base. Initial concentrations are 0.25, 0.17. This is 0. We ignored that one. Initial change equilibrium. This shifts to the right because I have a 0. So 0.17 plus x. And then the Ka is 4.9 times 10 to the negative 10. We can assume that x is small. So x times 0.17 divided by 0.25. Oh, that's small. 7.2. We want pH, so I'm not going to round much. And the negative log of that, (9.14). So that's the equilibrium method. And the Henderson-Hasselbalch approach, usually it gets written like this, is pH equals pKa plus log of base over acid. So pH equals pKa, which is 9.31, plus the log of my base concentration divided by my acid concentration. So 9.31 plus a negative 0.167491. So pH equals 9.14. So there's a lot less to write with the Henderson-Hasselbalch equation. Any questions? Any at all? Okay. So if we can calculate for a pH, or we can calculate the pH of a buffer system that's just like static. I make a buffer, this is what its pH is going to be. But what happens if we add something to that buffer system? And as long as we stay in the buffer range, it's actually very easy. Because when we're in the buffer range, we can use the Henderson-Hasselbalch equation. Adding a strong acid or a strong base is just like changing the initial concentrations of the buffer. So we break this down into two steps. The first part is the stoichiometry calculation. So if I add strong acid or if I add strong base, how much does that change my acid into base or my base into acid? Essentially, if I've got HA plus H2O, H3O plus A minus, adding strong acid to this will convert some of my base into acid. If I add a strong base, it'll convert some of my acid into a base. And then we do an equilibrium calculation based on our new starting amount. So adding strong acid, strong base just kind of changes the starting point for our pH calculation. So we've got a buffer that contains generic weak acid, generic weak base. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which statement is true? The relative concentrations of the weak acid and its conjugate base in the buffer. Yeah. We can kind of get this out of the Henderson-Hasselbalch equation, specifically this one that we did up here. So this is the base, this is the acid. If I divide those, I'm going to get a number that's smaller than 1. Right? Makes sense. Smaller number on top, larger number on the bottom, which means that when I take the log of that, I'm going to get a negative number. And so here I got negative 0.16749. So the ratio of my base to acid, because it's acid heavy, means that my pH is going to be lower than the pKa. So pKa is 9.31. Because I have more acid, my pH ends up lower than pKa. So then in this problem down here, the pKa, 4.82, but the pH is 4.25. Since that's lower, that means lower than pKa means more acid than the conjugate base. So I want you to do this. If my pKa here is separate thing, pKa equals 4.82. Okay, so let's see. HA equals 0.1. A minus equals 0.1. What is the pH? the concentrations are the same. When you plug them into the log, I get 0.1 divided by 0.1, which gives me 1. The log of 1 is 0. So when the concentrations of the acid and the concentrations of the base are the same, the pKa is the pH. And that also represents the middle point of our titration curve, at least in the, well, I say the middle point, but the flat spot in a titration curve. The middle of this is the pKa. It's in the middle because it's the exact same amount of acid and base. Yeah. So if we look at this example, we've got 1 liter of buffer, 0.1 molar in both acid and base, so pH equals pKa. Calculate the pH after adding 0.025 moles of strong acid. So when we add that strong acid in, I'm adding all of this H+, and so my H+ will react with the A-, the conjugate base, and turn it into more acid. This is not the equilibrium ice table. This would just be like a stoichiometry ice table where we're converting some of that A- into HA. You almost don't need to even do like a stoichiometry table or write out the stoichiometry for this, because it's always going to take away from one of these like it does here, and I'm moving it over to the other side. So one decreases, right? This decreased by, this was minus 0.025. This was plus 0.025. So it's not deleting it, it's moving it over. And it just, again, changes the initial point that we start our calculations from. So now I've got new calculations. I can set up an actual equilibrium ice table, or I could use the Henderson-Hasselbalch equation. Hmm. And at least in buffer solutions, because we're working in terms of concentration, if the volumes are the same, or the volumes will be the same because it's all in the same solution, then I can work in terms of moles instead of molarity. Or you just always work in terms of molarity. And then adding a small amount of base, or adding, yeah, a small amount of strong base is exactly the opposite. So now that's going to react with my acid. And so now my acid concentration will decrease by some amount, 0.025 in this case, and my base, conjugate base, will increase by 0.025. It's taking it from one column, moving it over to the other. I had actually calculated what the pH is, but they didn't give us a pKa. So I think overall, the key here is that adding strong acid or strong base, make that a capital B, changes the initial. Here we go. Nope. So it just changes our initial amounts, and then we can calculate the pH after that. But these are small amounts of strong acid and small amounts of strong base because we're still talking about this buffer zone. We're still within the nice, convenient walled garden of the buffer zone. We will venture outside of that, but this is like Tutorial Island in a video game. So as long as, exaggerated on this one, we start to get out to here, my pKa would be here. As long as my strong base added nudges inside of here and I don't leave that buffer region, or if I add a strong acid and it nudges this way, we just change the initial concentrations and then use like the Henderson-Hasselbalch, or you could do an equilibriumized table to figure out what our new pH is. And this is kind of the mental picture in my head of what's happening. When you add acid, I'm breaking off, so I'm adding acid here. I'm breaking off a chunk of this, and I am adding it on top of the acid. So whatever amount the base goes down by, the acid goes up by that amount. If you add base, it's just the opposite. I'm taking a chunk off of the acid, and I'm adding it to the base. So whatever the base goes up by is what the acid goes down by. Subtract from one, add to the other. Take it out of one pile and put it in the other pile. So which image, the A, B, or C on the left, best represents the amount of hydroxide added to the buffer in part B of the figure? You don't need this side. How many acids did I convert into a base? Just one. So A is if I'm adding, so if I add in a hydroxide here, then that's going to take the acid from, or the hydrogen from one of these acids and adds it to, so that was this one, adds it over to this column. So my acids decrease by 1, my bases increase by 1, which gives me that net change of 2. Right. Now the math. So a 1 liter buffer solution contains 0.1 moles of acetic acid, and they give us a Ka, and 0.1 moles of sodium acetate. So because our initial concentrations are equal, my pH equals my pKa of 4.74. So I want to calculate the new pH after adding 0.015 moles of sodium hydroxide. So if I have 0.100 moles of HC2H3O2, and I have 0.100 moles NaC2H3O2. what does adding base, strong base, do to those amounts of moles? Mhm. It'll reduce, because this is a base, it'll react with my acid. So that decreases by 1.5 moles. And of course, when I convert it to acetate, that's going to add it to the conjugate base. So this will go up by 0.015 moles. So now I've got 0.085 moles of HC2H3O2 and 0.115 moles of NaC2H3O2. And we can solve this without doing an ice table now. We just need the Henderson-Hasselbalch equation. pH equals pKa plus the log. The log of what? Base of the acid. And which base? Sodium hydroxide? Sodium acetate? Yeah. We already dealt with sodium hydroxide. Sodium hydroxide killed some of my acetic acid. So it's already dealt with. The Henderson-Hasselbalch equation deals with the concentrations of the acid in the base of the buffer system. So the weak acid, weak base. This will be 4.74 plus log of base over acid, 0.115. So is my pH going to be higher or lower than pKa? Higher. Because 0.115 divided by 0.085 is going to be larger than 1. So my log will be larger than 1. So pH equals 4.87. Yeah, 2 sig figs. So just as some of the things that I could see being common mistakes on a test, things like if you write out this and you have base over acid, forgetting which base to use. It's like putting the strong base in there instead of the weak base. There's another one. Or forgetting which order those go in, base over acid. But you can check because, I mean, yeah, you can look at this and say like, well, I've got, if I do this divided by this, 0.115 divided by 0.085, that's going to be larger than 1. That should give me a number, or pK, or pH, larger than my pKa. But also, if you look at the just concentrations of acid versus base, I have more base now than I have acid. My pH should go up. If your pH doesn't go up, then something in the math went wrong. Questions? Okay. So we can use weak bases and their conjugate acids as buffer systems. So ammonia and ammonium chloride here would be a buffer system, NH3 and NH4 plus. Oftentimes you're going to be given for this system, you would be given Kb, because on a table of values, Kb for NH3 would be given, but not necessarily the Ka for NH4 plus. So a couple ways that you can get the Ka, because the Henderson-Hasselbalch equation is pH equals pKa plus log of base over acid. We need pKa. So if you're given the pKb, just like pH plus pOH equals 14, pKa plus pKb equals 14. And it's for the same reason that Ka times Kb equals Kw. Just taking the negative log of all of that. You can rearrange the Henderson-Hasselbalch equation so that it works for pKb, but I think it's easier to memorize the one and then convert Ka to Kb if needed, or sorry, Kb to Ka. So I mean, with the weak base and its conjugate acid, it's the same thing as a weak acid and its conjugate base. Just have both in solution. So any base added reacts with the conjugate acid. Any acid added reacts with the base. And the concentrations or the calculations are going to be equally similar. I'm tired, and this coffee is supposed to have twice as much caffeine.
I'm not drinking it fast enough.
You're right. I need to drink it twice as fast, also for 4 times the energy. Used to be the joke with 5-hour energies, right? Drinking 10 5-hour energies for 50 continuous hours of energy. This doesn't know you probably will die. It's so much caffeine. And niacin and B12, B6, B12. Okay, so we can do this one real quick. A buffer solution that is 0.5 molar in NH3, ammonia, 0.2 molar in NH4. Oh, and we're adding some solid sodium hydroxide. Oh. Okay, let's write out the things that we have. We have 1.0 liters of solution. We have 0.50 molar NH3. And we have 0.20 molar NH4Cl. We add 0.010 moles of NaOH. It's like a real subtle thing, but it's important that it's solid because it doesn't change the volume. If we added liquid and the volume changes, we had to calculate some other stuff. And up until this point, we've done almost everything, and molarity or atmospheres and the units haven't mattered all that much. But you're going to have to start remembering to look at units again. Because, well, for this problem, it's 1 liter. So the 1 liter means that how many moles of ammonia do I have? 0.5. Molarity is moles over liters, so molarity times liters will give me moles. So this is 0.50 moles of NH3. This is 0.20 moles of NH4Cl. And which of those is the sodium hydroxide going to affect? Yeah. Because this is really NH4 plus. So when I add a base to that, it'll take one of those hydrogens. So I'm going to subtract 0.010 moles from there, and I'm going to add 0.01 moles to my ammonia. Because I'm converting some of the ammonium into ammonia. Ammonia. That's not how math works. Okay. Okay, we can almost do the Henderson-Hasselbalch equation. pH equals pKa plus log of, I'll put these in here, acid, or base over acid, base over acid. Oh, actually, we don't even know what the pKa is. So pKa plus pKb equals 14. So pK equals 14 minus 4.75. So we can put this in here, 9.25 plus whatever the log of that is. So pH equals 9.68. Does that answer make sense? Yeah. My pKa is 9.25, which would be equal amounts of base and acid. I have more base than acid, so I would expect my pK or my pH to be higher than the pKa.